Catalysis is the increase in the rate of a chemical reaction of one or more reactants due to the participation of an additional substance called a catalyst. Unlike other reagents in the chemical reaction, a catalyst is not consumed by the reaction. With a catalyst, less free energy is required to reach the transition state, but the total free energy from reactants to products does not change. A catalyst may participate in multiple chemical transformations. The effect of a catalyst may vary due to the presence of other substances known as inhibitors or poisons or promoters. The opposite of a catalyst, a substance that reduces the rate of a reaction, is an inhibitor. Catalyzed reactions have a lower activation energy than the corresponding uncatalyzed reaction, resulting in a higher reaction rate at the same temperature and for the same reactant concentrations. However, the mechanistic explanation of catalysis is complex. Catalysts may affect the reaction environment favorably, or bind to the reagents to polarize bonds, for example acid catalysts for reactions of carbonyl compounds, or form specific intermediates that are not produced naturally, such as osmate esters and osmium tetroxide-catalyzed dihydroxylation of alkenes, or cause dissociation of reagents to reactive forms, such as chemisorbed hydrogen in catalytic hydrogenation. Kinetically, catalytic reactions are typical chemical reactions. That is, the reaction rate depends on the frequency of contact to the reactants in the rate-determining step. Usually, the catalyst participates in this lowest step, and rates are limited by amount of catalyst and its activity. In heterogeneous catalysis, the diffusion of reagents to the surface and diffusion of products from the surface can be rate-determining. A nanomaterial-based catalyst is an example of a heterogeneous catalyst. Analogous events associated with substrate binding and product dissociation apply to homogeneous catalysts. Although catalysts are not consumed by the reaction itself, they may be inhibited, deactivated, or destroyed by secondary processes. In heterogeneous catalysis, typical secondary processes include coking, where the catalyst becomes covered by polymeric side products. Additionally, heterogeneous catalysts can dissolve into the solution in a solid or liquid system or sublimate in a solid or gas system. Background: the production of most industrially important chemicals involves catalysis. Similarly, most biochemically significant processes are catalyzed. Research into catalysis is a major field in applied science and involves many areas of chemistry, notably organometallic chemistry and materials science. Catalysis is relevant to many aspects of environmental science, for example the catalytic converter in automobiles and the dynamics of the ozone hole. Catalytic reactions are preferred in environmentally friendly green chemistry due to the reduced amount of waste generated, as opposed to stoichiometric reactions in which all reactants are consumed and more side products are formed. The most common catalyst is the hydrogen ion. Many transition metals and transition metal complexes are used in catalysis as well. Catalysts called enzymes are important in biology. A catalyst works by providing an alternative reaction pathway to the reaction product. The rate of the reaction is increased as this alternative route has a lower activation energy than the reaction route not mediated by the catalyst. The disproportionation of hydrogen peroxide creates water and oxygen, as shown below. 2 hours 2O2 or 2 hours 2O plus O2, this reaction is preferable in the sense that the reaction products are more stable than the starting material, though the uncatalyzed reaction is slow. In fact, the decomposition of hydrogen peroxide is so slow that hydrogen peroxide solutions are commercially available. This reaction is strongly affected by catalysts such as manganese dioxide, or the enzyme peroxidase in organisms. Upon the addition of a small amount of manganese dioxide, the hydrogen peroxide reacts rapidly. This effect is readily seen by the effervescence of oxygen. The manganese dioxide is not consumed in the reaction, and thus may be recovered unchanged, and reused indefinitely. Accordingly, manganese dioxide catalyzes this reaction. General principles, units. Catalytic activity is usually denoted by the symbol Z and measured in mole per second, a unit which was called Cal and defined the SI unit for catalytic activity since 1999. Catalytic activity is not a kind of reaction rate, but a property of the catalyst under certain conditions, in relation to a specific chemical reaction. Catalytic activity of 1 catal of a catalyst means an amount of that catalyst that leads to a net reaction of 1 mol per second of the reactants to the resulting reagents or other outcome which was intended for this chemical reaction. A catalyst may and usually will have different catalytic activity for several distinct reactions. See catal for an example. There are further derived SI units related to catalytic activity, see the above reference for details. Typical mechanism. Catalysts generally react with 1 or more reactants to form intermediates that subsequently give the final reaction product, in the process regenerating the catalyst. The following is a typical reaction scheme, where C represents the catalyst, X and Y are reactants, and Z is the product of the reaction of X and Y, X plus ClXC, Y plus XClXYC, XYC is CZ, CZ is C plus Z. Although the catalyst is consumed by reaction 1, it is subsequently produced by reaction 4, so for the overall reaction, X plus Y is Z, as a catalyst is regenerated in a reaction, often only small amounts are needed to increase the rate of the reaction. In practice, however, catalysts are sometimes consumed in secondary processes. As an example of a detailed mechanism at the microscopic level, in 2008 Danish researchers first revealed a sequence of events when oxygen and hydrogen combine on the surface of titanium dioxide to produce water. With a time-lapse series of scanning tunneling microscopy images, they determined the molecules undergo adsorption, dissociation and diffusion before reacting. The intermediate reaction states were HO2, H2O2, then H3O2 and the final reaction product, after which the water molecule desorbs from the catalyst surface. Reaction energetics. Catalysts work by providing a mechanism involving a different transition state and lower activation energy. Consequently, more molecular collisions have the energy needed to reach the transition state. Hence, catalysts can enable reactions that would otherwise be blocked or slowed by a kinetic barrier. The catalyst may increase reaction rate or selectivity, or enable the reaction at lower temperatures. This effect can be illustrated with an energy profile diagram. In the catalyzed elementary reaction, catalysts do not change the extent of a reaction, they have no effect on the chemical equilibrium of a reaction because the rate of both the forward and the reverse reaction are both affected. The second law of thermodynamics describes why a catalyst does not change the chemical equilibrium of a reaction. Suppose there was such a catalyst that shifted an equilibrium. Introducing the catalyst to the system would result in a reaction to move to the new equilibrium, producing energy. Production of energy is a necessary result since reactions are spontaneous if and only if Gibbs free energy is produced, and if there is no energy barrier, there is no need for a catalyst. Then, removing the catalyst would also result in reaction, producing energy. That is, the addition and its reverse process, removal, would both produce energy. Thus, a catalyst that could change the equilibrium would be a perpetual motion machine, a contradiction to the laws of thermodynamics. If a catalyst does change the equilibrium, then it must be consumed as the reaction proceeds, and thus it is also a reactant. Illustrative is the base-catalyzed hydrolysis of esters, where the produced carboxylic acid immediately reacts with the base catalyst and thus the reaction equilibrium is shifted towards hydrolyses. The SI-derived unit for measuring the catalytic activity of a catalyst is the catal, which is moles per second. The productivity of a catalyst can be described by the turnover number and the catalytic activity by the turnover frequency, which is the ton per time unit. The biochemical equivalent is the enzyme unit. For more information on the efficiency of enzymatic catalysis, see the article on enzymes. The catalyst stabilizes the transition state more than it stabilizes the starting material. It decreases the kinetic barrier by decreasing the difference in energy between starting material and transition state. It does not change the energy difference between starting materials and products, or the available energy. Materials. The chemical nature of catalysts is as diverse as catalysis itself, although some generalizations can be made. Proton acids are probably the most widely used catalysts, especially for the many reactions involving water, including hydrolysis and its reverse. Multifunctional solids often are catalytically active, for example xylides, alumina, higher-order oxides, graphitic carbon, nanoparticles, nanodots, and facets of bulk materials. Transition metals are often used to catalyze redox reactions. Examples are nickel, such as Raney nickel for hydrogenation, and vanadium, V, oxide for oxidation of sulfur dioxide into sulfur trioxide by the so-called contact process. Many catalytic processes, especially those used in organic synthesis, require late transition metals, such as palladium, platinum, gold, ruthenium, rhodium, or iridium. Some so-called catalysts are really pre-catalysts. Pre-catalysts convert to catalysts in the reaction. For example, Wilkinson's catalyst are HCl, PPH3, 3 loses 1-triphenylphosphine ligand before entering the true catalytic cycle. Pre-catalysts are easier to store but are easily activated in situ. Because of this pre-activation step, many catalytic reactions involve an induction period. Chemical species that improve catalytic activity are called co-catalysts or promoters in cooperative catalysis. Types: catalysts can be heterogeneous or homogeneous, depending on whether a catalyst exists in the same phase as the substrate. Biocatalysts are often seen as a separate group. Heterogeneous catalysts. Heterogeneous catalysts act in a different phase than the reactants. Most heterogeneous catalysts are solids that act on substrates in a liquid or gaseous reaction mixture. Diverse mechanisms for reactions on surfaces are known, depending on how the adsorption takes place. The total surface area of solid has an important effect on the reaction rate. The smaller the catalyst particle size, the larger the surface area for a given mass of particles. For example, in the Haber process, finely divided iron serves as a catalyst for the synthesis of ammonia from nitrogen and hydrogen. The reacting gases adsorb onto active sites on the iron particles. Once adsorbed, the bonds within the reacting molecules are weakened, and new bonds between the resulting fragments form in part due to their close proximity. In this way, the particularly strong triple bond in nitrogen is weakened and the hydrogen and nitrogen atoms combine faster than would be the case in the gas phase, so the rate of reaction increases. Another place where a heterogeneous catalyst is applied is in the oxidation of sulfur dioxide on vanadium, V, oxide for the production of sulfuric acid. Heterogeneous catalysts are typically supported, which means that the catalyst is dispersed on a second material that enhances the effectiveness or minimizes their cost. Supports prevent or reduce agglomeration and sintering of the small catalyst particles, exposing more surface area, thus catalysts have a higher specific activity on a support. Sometimes the support is merely a surface on which the catalyst is spread to increase the surface area. More often, the support and the catalyst interact, affecting the catalytic reaction. Supports are porous materials with a high surface area, most commonly alumina, xylides or various kinds of activated carbon. Specialized supports include silicon dioxide, titanium dioxide, calcium carbonate, and barium sulfate. Electra Catalysts. In the context of electrochemistry, specifically in fuel cell engineering, various metal-containing catalysts are used to enhance the rates of the half reactions that comprise the fuel cell. One common type of fuel cell electrocatalyst is based upon nanoparticles of platinum that are supported on slightly larger carbon particles. When in contact with one of the electrodes in a fuel cell, this platinum increases the rate of oxygen reduction either to water, or to hydroxide or hydrogen peroxide. Homogeneous catalysts. Homogeneous catalysts function in the same phase as the reactants, but the mechanistic principles invoked in heterogeneous catalysis are generally applicable. Typically, homogeneous catalysts are dissolved in a solvent with the substrates. One example of homogeneous catalysis involves the influence of H+ on the esterification of carboxylic acids, such as the formation of methyl acetate from acetic acid and methanol. For inorganic chemists, homogeneous catalysis is often synonymous with organometallic catalysts. Organocatalysis. Whereas transition metals sometimes attract most of the attention in the study of catalysis, small organic molecules without metals can also exhibit catalytic properties, as is apparent from the fact that many enzymes lack transition metals. Typically, organic catalysts require a higher loading than transition metal, ion-based catalysts, but these catalysts are usually commercially available in bulk, helping to reduce costs. In the early 2000s, these organocatalysts were considered new generation, and are competitive to traditional metal, ion-containing catalysts. Organocatalysts are supposed to operate akin to metal-free enzymes utilizing, for example, non-covalent interactions such as hydrogen bonding. The discipline organocatalysis is divided in the application of covalent and non-covalent organocatalysts referring to the preferred catalyst substrate binding and interaction, respectively. Enzymes and biocatalysts. In biology, enzymes are catalysts in metabolism and catabolism. Most biocatalysts are protein-based, that is enzymes, but other classes of biomolecules also exhibit catalytic properties including ribozymes, and synthetic deoxyribozymes. Biocatalysts can be thought of as intermediate between homogeneous and heterogeneous catalysts, although strictly speaking soluble enzymes are homogeneous catalysts and membrane-bound enzymes are heterogeneous. Several factors affect the activity of enzymes including temperature, pH, concentration of enzyme, substrate, and products. A particularly important reagent in enzymatic reactions is water, which is the product of many bond-forming reactions and a reactant in many bond-breaking processes. In biocatalysis, enzymes are employed to prepare many commodity chemicals including high-fructose corn syrup and acrylamide. Significance. Estimates are that 90% of all commercially produced chemical products involve catalysts at some stage in the process of their manufacture. In 2005, catalytic processes generated about $900 billion in products worldwide. Catalysis is so pervasive that sub-areas are not readily classified. Some areas of particular concentration are surveyed below. Energy processing. Petroleum refining makes intensive use of catalysis for alkylation, catalytic cracking, naphtha reforming and steam reforming. Even the exhaust from the burning of fossil fuels is treated via catalysis. Catalytic converters, typically composed of platinum and rhodium, break down some of the more harmful byproducts of automobile exhaust. 2CO plus 2NO or 2CO2 plus N2. With regard to synthetic fuels, an old but still important process is the Fischer-Tropsch synthesis of hydrocarbons from synthesis gas, which itself is processed via water-gas shift reactions, catalyzed by iron. Biodiesel and related biofuels require processing via both inorganic and biocatalysts. Fuel cells rely on catalysts for both the anodic and cathodic reactions. Catalytic heaters generate flameless heat from a supply of combustible fuel. Bulk chemicals. Some of the largest-scale chemicals are produced via catalytic oxidation, often using oxygen. Examples include nitric acid, sulfuric acid, terephthalic acid from peroxylene, and acrylonitrile from propane and ammonia. Many other chemical products are generated by large-scale reduction, often via hydrogenation. The largest-scale example is ammonia, which is prepared via the Haber process from nitrogen. Methanol is prepared from carbon monoxide. Bulk polymers derived from ethylene and propylene are often prepared via Ziegler-Natta catalysis. Polyesters, polyamides, and isocyanates are derived via acid-base catalysis. Most carbonylation processes require metal catalysts. Examples include the Monsanto acetic acid process and hydroformylation. Fine chemicals. Many fine chemicals are prepared via catalysis. Methods include those of heavy industry as well as more specialized processes that would be prohibitively expensive on a large scale. Examples include olefin metathesis using Grube's catalyst, the Heck reaction, and Friedel-Crafts reactions. Because most bioactive compounds are chiral, many pharmaceuticals are produced by enantiose elective catalysis. Food processing. One of the most obvious applications of catalysis is the hydrogenation of fats using nickel catalyst to produce margarine. Many other foodstuffs are prepared via biocatalysis. Environment. Catalysis impacts the environment by increasing the efficiency of industrial processes, but catalysis also plays a direct role in the environment. A notable example is the catalytic role of chlorine-free radicals in the breakdown of ozone. These radicals are formed by the action of ultraviolet radiation on chlorofluorocarbons. Cl plus O3 a ClOA plus O2, ClOA plus O a Cl plus O2. History. In a general sense, anything that increases the rate of a process is a catalyst, a term derived from Greek II plus or minus II plus or minus III micron I to the first I 1/2, meaning to annul, or to untie, or to pick up. The term catalysis was coined by Jar paragraph N.S. Jacob Berzelius in 1835 to describe reactions that are accelerated by substances that remain unchanged after the reaction. Other early chemists involved in catalysis were Ilhad Mitscherlich, who referred to contact processes, and Johann Wolfgang Dar paragraph Beriner, who spoke of contact action and whose lighter based on hydrogen and a platinum sponge became a huge commercial success in the 1820s. Humphrey Davy discovered the use of platinum in catalysis. In the 1880s, Wilhelm Ostwald at Leipzig University started a systematic investigation into reactions that were catalyzed by the presence of acids and bases, and found that chemical reactions occur at finite rates and that these rates can be used to determine the strengths of acids and bases. For this work, Ostwald was awarded the 1909 Nobel Prize in Chemistry. Inhibitors, poisons and promoters. Substances that reduce the action of catalysts are called catalyst inhibitors if reversible, and catalyst poisons if irreversible. Promoters are substances that increase the catalytic activity, even though they are not catalysts by themselves. Inhibitors are sometimes referred to as negative catalysts since they decrease the reaction rate. However, the term inhibitor is preferred since they do not work by introducing a reaction path with higher activation energy. This would not reduce the rate since the reaction would continue to occur by the non-catalyzed path. Instead, they act either by deactivating catalysts, or by removing reaction intermediates such as free radicals. The inhibitor may modify selectivity in addition to rate. For instance, in the reduction of acetylene to ethylene, a palladium catalyst partly poisoned with lead, acetate can be used. Without the deactivation of the catalyst, the ethane produced will be further reduced to ethane. The inhibitor can produce this effect by, for example, selectively poisoning only certain types of active sites. Another mechanism is the modification of surface geometry. For instance, in hydrogenation operations, large planes of metal surface function as sites of hydrogenolysis catalysis, while sites catalyzing hydrogenation of unsaturates are smaller. Thus, a poison that covers surface randomly will tend to reduce the number of uncontaminated large planes but leave proportionally more smaller sites free, thus changing the hydrogenation versus hydrogenolysis selectivity. Many other mechanisms are also possible. Promoters can cover up surface to prevent production of a matte of coke, or even actively remove such material. They can aid the dispersion of the catalytic material or bind to reagents. Current market. The global demand on catalysts in 2010 was estimated at approximately $29.5 billion USD. With the rapid recovery in automotive and chemical industry overall, the global catalyst market is expected to experience fast growth in the next years. See also: Autocatalysis, Big NSE, Catalysis Science and Technology, Environmental Triggers, Enzyme Catalysis, Industrial Catalysts, Kelvin Probe Force Microscope, Pharmaceutic Adjuvant, Phase Boundary Catalysis, Phase Transfer Catalyst, Photocatalysis, Ribozyme, Sumo Enzymes, Temperature Programmed Reduction, Thermal Desorption Spectroscopy. References: IUPAC, Compendium of Chemical Terminology, 2nd ed. Online corrected version, 2006. A Euro Catalyst. External links: Science Aid, Catalysts page for high school level science, W. A. Harriman Technische Universität Currency T. Presentation, Alumite Catalyst, Kamiyama Sakurai Laboratory, Japan, Inorganic Chemistry and Catalysis Group, Utrecht University, the Netherlands Centre for Surface Chemistry and Catalysis, Carbons and Catalysts Group, University of Concepcion, Chile, Center for Enabling New Technologies Through Catalysis, and NSF Center for Chemical Innovation, USA, Bubbles Turn on Chemical Catalysts, Science News Magazine Online, April 6, 2009.